Okay, so in the last class we discussed first order differential equation, mainly variable separable differential equation and homogeneous differential equation. In the today's class we will discuss first order exact differential equation. So let us try to solve the differential equation y dx minus x dy by x square is equal to 0. So if you see it, it is not a variable separable and may not easily be transformed into variable separable or homogeneous differential equation. But it is very easy to solve if we write it as minus d of y by x is equal to 0. So the left hand side is a differentiation of y by x only with a negative sign, and now if you integrate both the sides, then it becomes minus y by x is equal to c. It means that if a given differential equation m dx plus n dy is equal to 0 can be expressed as d of f is equal to 0, then we call it an exact differential equation whose solution is f of xy is equal to c. Let's try one more question. Y 2xy plus e raised to the power x dx is equal to e raised to the power x dy. First try to check, we do not know any method to check which we will study, is the given equation exact or how do you solve it, because again variable separable homogeneous does not work here. So this equation can be written as 2xy square dx plus y e raised to the power x dx minus e raised to the power x dy is equal to 0. Now this y square is creating problem, which means if I multiply the given differential equation, so equation 1 by 1 by y square, let's see what will happen. So the given differential equation becomes 2x dx plus e raised to the power x by y dx minus e raised to the power x y square dy is equal to 0. Yes, so the first term is as it is, but the second term is differentiation of e raised to the power x by y dy is equal to 0. Or you can write it as the given differential equation is differentiation of e raised x square plus e raised to the power x by y dy is equal to 0. So now initially the given equation is not exact, but you multiply it with a function of x comma y, which is integrating factor, and the equation becomes exact. So in this section we are going to study how to check the differential equation is exact. If it is exact, how to solve it. If it is not exact, can it be made exact by introducing the integrating factor. So how do we find the integrating factor? So to begin with, first we need to see the definition of exact and the necessary and sufficient condition for the exactness. So let us consider that you have given a function f of x comma y is equal to c, a constant. This is the solution which you are actually looking for, which simply means that d of f is equal to 0, and d of f can be written as del f by del x dx plus del f by del y dy is equal to 0. Yes, so if you compare it with the m dx plus n dy is equal to 0, then m is equal to del f by del x and n is equal to del f by del y. Now m dx plus n dy is equal to 0, which is same as df is equal to 0, because you have said this equation as m dx plus n dy is equal to 0. So this gives you df is equal to 0, which means that f of x comma y is equal to c. This is c. So if you see the other way around, it means that if the given differential equation is m dx plus n dy is equal to 0, and you can write it as d of f is equal to 0, then you can solve it as f of x comma y is equal to c, which means that we can say if m dx plus n dy is equal to d of f, then it has a general solution f of x comma y is equal to c, and this is known as the exact differential equation. But how do we know, or how do we check the given differential equation is exact or not? So we say that the differential equation m dx plus n dy is equal to 0 is exact if and only if del m by del y is equal to del n by del x, where m and n have continuous first order partial derivatives. So this concept of continuous first order partial derivative would come in the proof. Otherwise you simply need to remember that m dx plus n dy is equal to 0 is exact if and only if del m by del y is equal to del n by del x, which means if del m by del y is not equal to del n by del x, then the equation is not exact. Let's quickly go through the proof. So first we will show that the given differential equation is exact, and then del m by del y should be equal to del n by del x. So if it is exact, then it can be written as df, which means m dx plus n dy should be equal to df, where df is del f by del x dx plus del f by del y dy, which means m is equal to del f by del x and n is equal to del f by del y. But I need to show that del m by del y is equal to del n by del x. So I have m and n now. So let's compute del m by del y and del n by del x. So del m by del y comes out to be del 2f by del y del x, and del n by del x, del n by del x comes out to be del 2f by del y del x. You can see that at this stage del m by del y is not equal to del n by del x, which means under what condition del 2f by del y del x is equal to del 2f del y del x. Sorry, this is del by del x, so this is x and this is y. So under what condition del 2f by del x del y is equal to del 2f del y del x? Yes, now if you recall that, then there is a result which says that if f has continuous second order partial derivatives, then del 2f by del y del x is equal to del 2f by del x del y. Yes, so now the next question, does f has second order continuous partial derivatives? Yes or no? So here we can quickly make changes so that there should not be any confusion. Meanwhile, you can think that does f has continuous second order partial derivative? So del m by del y, this is del y del x, and this is del x del y. Yes, so now recall that what is given. So it is given that m and n have first order continuous partial derivative, and what is m? Del f by del x, which is differentiation of f with respect to x, and similarly n is differentiation of f with respect to y. So if m and n have first order continuous partial derivative, it means f has second order continuous partial derivative, and therefore del 2f by del y del x is same as del 2f by del x del y. That gives you del m by del y is equal to del n by del x. So one side proof. The second side is little bit tricky, where we need to show that if del m by del y is equal to del n by del x, then the equation is exact. Now exact means that we need to show that we must be able to construct f such that df is equal to 0. Yes, and what we have given? We have given del m by del y is equal to del n by del x. So using this we need to construct f. So now we need to construct a function f such that, or you can say capital F, such that m dx plus n dy is equal to df, where m is del f by del x, n is del f by del y. If you would be able to construct such f, then we say the given differential equation is exact. Now I have given m is equal to del f by del x. If I integrate with respect to x, then f becomes del m integration m dx plus g of y. Again I have the another condition, n is equal to del f by del y, which means if I differentiate equation 1 with respect to y, this should be equal to n. So let's differentiate it. So after differentiating it, I get g dash y is equal to n minus del by del y integration m dx, or g of y is as follows. Now the interesting observation is, this is my g of y. It means that my f should be this one, integration m dx plus g of y. And this f satisfy the given conditions. So given conditions means del m by del y is equal to del n by del x. There is only one issue, that this g of y which I obtained is a function of y. The left hand side is a function of y, but I do not know that is the right hand side is a function of y. So to make sure that this f is equal to integration m dx plus g of y satisfy the given conditions, I must confirm that the right hand side is a function of y. Yes, so it is a function of y. To show it is a function of y, I just need to show that its differentiation with respect to x is 0. So let's differentiate it with respect to x. So if I differentiate it with respect to x, it becomes del n by del x minus del 2 by del x del y integration m dx. Now if I can write del 2 by del x del y as del 2 by del y del x, then it simply becomes del n by del x minus del m by del y, and I have given del n by del x is equal to del m by del y, and therefore it would become equal. But why is it so? Why del 2 by del x del y here should be equal to del 2 by del y del x? Yes, so quickly see here, what is my integration m dx? I just computed it, that integration m dx is f minus g of y. See equation 1. Yes, now if I compute del 2 del x del y m dx, then it simply becomes, you differentiate f with respect to y and then with respect to x. When you differentiate g of y with respect to y, it becomes g dash y, and when you differentiate with respect to x, it becomes 0. So this simply becomes del 2f by del x del y. Now f has continuous second order partial derivatives, therefore this becomes del 2 del y del x of f, and which is again del 2 del y del x of integration m dx. Yes, so using this logic, I put it back here, and that gives me del n by del x, and this terms becomes del m by del y. It is given that del n by del x is equal to del m by del y, that's why this is equal to 0, which we need to prove. And now we can say that the obtained function f satisfy both the conditions, and therefore it satisfies both the conditions, and therefore del m by del y is equal to del n by del x gives us an exact differential equation. Okay, so the most important observation here is that if m dx plus n dy is equal to 0 is exact, then its solution is f of x comma y is equal to c, where f is given as follows. So this you need to remember it. It would be clear once we do this exercise. So check if the given differential equation is exact, and if it is, then solve it. To check it is exact, I need to see that what is, this is x, sorry. So what is m? So m is e raised to the power y, and n is x e raised to the power y plus 2y. So my del m by del y is e raised to the power y, and del n by del x is e raised to the power y. Both are equal. The given differential equation is exact, and its solution is integration m dx plus integration n minus del by del y integration m dx dy is equal to c, which is f is equal to c. So if you substitute the values, m is e raised to the power y dx plus what is n, x e raised to the power y plus 2y, and then the differentiation of integration m dx. So integration m dx, or let's write the values. So m dx, m is e raised to the power y, which is a constant, so this becomes x e raised to the power y, and dy is equal to c. Now the first term becomes x e raised to the power y plus integration x e raised to the power y plus 2y minus x e raised to the power y dy is equal to c. These two terms would cancel out. It simply becomes x e raised to the power y plus y square is equal to c. So you can see that it was quite easy to solve if you know the given differential equation is exact. You just need to remember this formula. We will do many exercises in the coming class. Thank you.